Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we will conclude Chapter 6 on nonparametric methods, discussing the permutation test. So I love permutation tests because it's a strategy to give you effectively exact p-values only using the assumptions that are provided in the null hypothesis. So it is a type of nonparametric statistics, permutation tests. And the basic premise is only to use the assumption that it is possible that all of the treatment groups are equivalent and that every member of them is the same before sampling began. That is, the position in the group to which they belong is not differentiable from any other position before the positions are filled. Meaning, if I'm taking a sample of size 10 and I draw one observation and put it in position 1 of my 10 observations, and then draw a second observation and put it in position 2, that those are exchangeable positions. Okay. Effectively, there's no time component to the samples. From this, one can calculate a statistic and then see to what extent this statistic is special by seeing how likely it would be if the group assignments had been jumbled, whether you belong to one sample versus another. So a permutation test, also called a randomization test or a re-randomization test or an exact test, is a type of statistical significance test in which the distribution of the test statistic under the null hypothesis is obtained by calculating all the possible values, or an approximation to that, of the test statistic under rearrangement of the labels of the observed data points. So if we, so here we go. In other words, the method by which the treatments are allocated to subjects in an experimental design is mirrored in the analysis of that design. Okay, so when you, going off script, so when you do randomization and I've got, say 20 participants and I want to randomize those 20 participants into two groups of 10 people, when you randomize them into the treatments, that's the randomization process. So some subset of 10 were treatment A, the other 10 became in treatment B, and before they were assigned to the treatments, there was that randomness that allocated to them to those two groups. Now, if the two treatments are equivalent, then it doesn't matter whether they got treatment A or treatment B, their outcome is going to be the same. Therefore, I can rearrange the labels, meaning whether someone is labeled A or B in the test, and compare and use that as the reference null distribution. Okay, so those are the ideas. All right. And these methods were developed back in the 30s by Pittman and Ron Fisher. And let's take a look at an example using the meteorites data to perform a permutation test. So suppose we've got two groups, the UWET and the Walker samples, and they each have certain sample means, y bar U for UWET and y bar W for Walker, and we want to test whether there's a difference between these two means. Alright, so we had 9 observations for the UWET and 10 observations for the Walker samples, and the permutation test is designed to determine whether the observed difference between the two sample means is large enough to reject the null hypothesis that the means are equal. Okay, so here's how the test proceeds. First, we calculate the observed statistic. So in our data set, the met.long from earlier in the chapter, we have in the second column is the observed values, and we also have a site column, and so I'm going to subset all the UWET values, output the actual values there, the cooling rates, and calculate the mean. So this first line is, to my eyes right now, a fairly clumsy way of calculating the mean of the UWET values. The second mean is the mean of the Walker observations, and the subtraction takes the difference. So this is our observed statistic, which we're calling t. So t observed is our observed statistic. The observed difference is 0.25. So now the question is 0.25 extreme compared to a null distribution? And so we are now going to construct an approximation of the null distribution by doing the permutation strategy. All right, so next, the difference in sample means is calculated and record for every possible way of dividing these pooled values into two groups of size 9 for the UWet and 10 for the Walker. So there happens to be a lot of ways you can permute these values. In fact, roughly 10 to the 17 is a little too many. So we're going to approximate that by taking a random sample. So in the code below, I have tons of comments, and we'll just walk through the logic here so you can understand the process. So the plan is to initialize a vector to store all the differences in means. So if I scroll up for a moment, the statistic that we're looking at is the difference in means. So that's what's calculated here. And our observed statistic comes from the actual labels of the UWet mean minus the Walker mean. But now I'm going to permute the labels of UWet and Walker among the 19 observations to get random subsets that are assigned to the UWet label, samples of size 9, and then samples of size 10, which are randomly assigned the Walker label. Take those differences, that we should expect that they're going to be centered at 0 and will have some variability, and then we're going to ask the question, is 0.25 unusual under the null hypothesis, which is the standard way that we assess hypothesis tests, whether we use the t-distribution or other distributions. So we're going to calculate a bunch of differences in means. R is going to be the number of repetitions. We'll do, looks like we're doing 10,000 of those. And so we're first going to initialize a vector of NAs. There'll be 10,000 of them. And that's going to be our t-perm, our permutation version of each for our null distribution of our statistic t. Then for each repetition, 1 to 10,000, we need to permute the labels. So this sample.integer of 19 gives us a set of numbers that are in random order. So we've got the digits 1 to 19, and we're going to randomize them. So they might be in the order 13, 9, 3, 4, 12, and so on. Then we're going to determine which values of our 19 we're going to assign to UWet. So if, let's see what we got here. Some site. So this says how many observations are in the UWet values, and these are basically the numbers 1 through 9. And if wherever those indices were less than or equal to 1 to 9, or just 9, less than or equal to 9, those are the indices that will be randomly assigned to the UWet. Similarly, anything that was not a UWet will be called Walker. And so lab U and lab W are the UWet and Walker labels, which are vectors of length 19 that have 9 trues and 10 trues in those random locations. Finally, we're going to find the values that are labeled true for UWet and calculate the mean, and then do the same thing for the Walker labels. Take those difference, and that becomes the t-statistic under the permutation for the ith repetition. Do that loop 10,000 times, and then we can make some comparisons. So I'm making a plot here by putting the permutation values into a data frame and then plotting that. So let's take a look at our null distribution. It's not a normal distribution. It's not skewed. It's really symmetric. It's almost like a triangular distribution. It's centered at 0. It basically has to be because we're permuting the labels, so where the Walker center and where the UET center is under the permutation they're basically equal, and so the difference is going to be 0. So it's centered at 0, and it has this certain distribution, and the red dashed line is the observed the observed difference in means. And finally, if we want to calculate the p-value, we calculate the how many observations in our permutation, or what proportion of them is more extreme than what we observed. That's the standard definition of a p-value. So we can calculate a one-sided upper p-value, a one-sided lower p-value, or a two-sample p-value. And in this case, because we're not coming to this problem with a certain hypothesis of whether one is greater than the other, the two-sided p-value is appropriate. Here is here's the value, 0.12. So under the permutation test, we don't have sufficient evidence to claim that the cooling rates between these two meteorites are equal, or are different, excuse me. It's basically consistent with them being equal. All right. Just for comparison, when we did our t-tests for this, our pooled p-value or Sadowitz weight, right, unequal variance p-value were both about the same. It was only with the Wilcox and Mann-Whitney test that we got something that was a little bit less. But okay. Permutation tests also allow you to construct confidence intervals and things like that, but I'm not showing that here. The second part of this video is going to say how this permutation idea can be extended to linear models. And there used to be a package called LM-Perm for linear model permutation, but it's been discontinued. So the COIN packages is now the way of doing permutation tests, and it's been really pretty easy to use. So let's just see an example of how to use this. The big step for us in Advanced Data Analysis 1 is to reformulate our t-tests, our two-sample t-test, as a linear model. And this is something that we'll all become experts in the second semester of Advanced Data Analysis 2. But here's the basic idea. So in the t-test, we've got the cooling rate, which is the response, and we're going to make a comparison by site. So we've got the UET and the Walker as sites. They're categorical variables, and that specifies which cooling values come from which site, and the t-test knows to combine all the cooling rates from one site and compare that to all the cooling rates from another site. So we can use the same formula in this function LM for linear model. And here we've got the response cooling rate, and we have an effect, which is site. Okay, and just to take a look at what the results were, the p-value for the t-test was 0.1134. Okay, so let's scroll down and take a look at the summary from the linear model, which I'm putting into lm.summary. So here we have two coefficients, and this is not going to be a comprehensive discussion of linear models. We're going to have an opportunity to do that in Chapter 8 and then a lot next semester. But we have an intercept, which is basically like the mean for the baseline group. In this case, that's the UWET mean. And then we have a site Walker estimate, which is the offset between the baseline group, the UWET, and the Walker. So the difference between these two groups are negative 0.25. And that's a value we've seen before. And then this p-value, 0.1134, is telling us whether this difference, the 0.25, is statistically different from 0, given this t-statistic of negative 1.669. So if we scroll up to the t-test, we're going to see that p-value. We're going to see the difference between these two being 0.25. Here's that same t-statistic. So all the same statistics are coming up whether we do a t-test or whether we fit this linear model. And that's true because the linear model does make this assumption, this equal variance assumption. Okay, this doesn't work with the Satterthwaite approximation. So that being said, here's a way of doing the t-test using the linear model. And what if we didn't want to make normality assumptions? Well, we could use the COIN library and perform this one-way test. So we've got the cooling rate by site, and it actually, as it computes, determines how many observations or permutation values it needs to generate a p-value that's accurate enough to use an inference. Here we have a p-value of 0.11. How does that compare to what we observed before? 0.113. Okay, this is 0.1114. Big deal. They're basically the same. And so we have inference, but here we have not made any model assumptions for normality. So that's a real advantage. If we had really skewed data or something unusual, we could still use this strategy. All right, so I have more information about this. I show how to do this when we've got more levels. For example, in the automobile emissions example, and I invite you to read those. The last section in this chapter, which I won't really discuss here, is on density estimation. And the basic idea of density estimation, and we've seen density estimates since the beginning of class. It's how do you take a histogram or individual observations, right? So we have individual let me back up one little moment here. All right. So here there's some individual observations, and these 5 histograms are 5 ways of summarizing the same data, and all we're doing is changing the number of breaks or the number of bins that we have to capture the data. And you can see there's some cases where there aren't enough breaks, and there's some cases where there are far too many. And so we're thinking about how do we use the histogram bin width to give us a smooth representation of the data so that we can interpret skewness, center, spread, all those types of statistics. And this is really simple to do in R. We just use the histogram command and specify different numbers of breaks to get those. The default tends to work pretty well. Sometimes I think it ends up being the bins maybe are a little too wide. So specifying some additional breaks sometimes gives you the resolution you need to make some determinations about skewness or outliers. What a density plot does is it performs a similar idea, but instead of using rectangles, it actually adds together a bunch of like normal distributions or some other kernel. So let me zoom in a little bit. In the plots below, we're going to create a density plot, and we're going to specify different bin widths. And so the top plot does this using the default. The one below has a very narrow bin width, and the one at the very bottom has a very wide bin width. So effectively, for every observation that we have, we're going to fit a normal distribution. So we have a bunch of little normal distributions centered at every observation. We're going to add them all up. And when you add up a bunch of small normal distributions, it looks like a big sort of smooth distribution. When we have a normal distribution with a very small variance, then we get lots of wiggles because you can see the peak of where every of each observation lives. And when you have individual normal distributions that are very wide and you add them together, they end up over smoothing. Okay? And so the trick when you're doing density estimation is to find a good kernel, so for example a normal distribution to represent each point, and then to determine the characteristics of that normal distribution in terms of how smooth it is, or what the standard deviation is of each of those. If it's too narrow, you end up seeing too many wiggles, and if it's too wide, you don't really capture the features of the data. And you can also pick different kernels. The Gaussian is the normal distribution. There's two other ones here, and here's the same data summarized with three different kernels. Okay, so there are choices to make. The defaults that are designed in R and other software packages tend to work pretty well, but sometimes you want to have a little more control over the features that you observe in a density histogram. For example, in this middle plot, this is probably a little too fine resolution, but the point is that by changing the bin width, I can see more features, and sometimes that's helpful for making determinations of features in your data. All right, so that concludes Chapter 6 on nonparametric methods. Thanks for listening.